Here we find ourselves in section 4.3, which is all about rational functions, which you've already seen a little bit of in this class. Rational functions are functions that have fractional components, and they'll start you out with some relatively easy problems where you're just finding the domain. That may have to work for some of the outputs, but it should be relatively straightforward because it's something that you practiced in your intermediate algebra class. So for example, the first example that we'll do today, example number 1, they just simply want you to find the domain. They want to make sure that you remember that we've dealt with rational functions before. I'll call it capital G of x. Usually with rational functions they use capital letters. Capital G's, F's, Q's, R's are used as well. And so in this function they had, or this problem that I saw in the homework, they had this, but they left the bottom unfactored. 6x squared minus 41x plus 7. Oh, apologize, it's not going to be plus 7. Let me fix that really quick. It's going to be a minus 7. So let me make that a minus. And so as that happens, we're just going to say, well, if I'm going to identify the domain, I need to know where the bottom 0. In order to find out where the bottom 0, I need to factor it. And then hopefully you're able to factor that. Hopefully you're able to say, well, personally, what I would say is 6 times 7 is 42. Are there factors of 42 that subtract to be 41? Yeah. And so I know it's going to be a 6x and an x. I know the 6 is going to hit a 7 to make a 42, and a 1's here. I need the 42 to be negative and the 1 to be positive. So we're thinking that you're very quick to factor. If factoring is a struggle for you, you really want to work to improve that skill, because a lot of what they give us can be factored, and you'll see that today and absolutely in the future. And so they want you to state the domain. So the domain, I noticed in this problem that they wanted it in what we call not interval notation, I apologize, like standard notation, set notation, that's it, set notation. I'm like, that doesn't really make sense either. So the domain is a set of all x such that x cannot be negative 1/6 and x cannot be 7. You see that happening? It can be anything else, just not either one of those two things. So the reason why we've cared for so long about domains is if negative 1/6 and 7 are not part of that domain, well, then there's the graph can't cross that, and we have what's called a vertical asymptote. And so we need to start talking a little bit about asymptotes. So you'll have some domain questions right away, and then you'll get to the heart of what's in 4.3, what's being taught in this pre-calculus class. So let me write out the word asymptotes. There are three kinds of asymptotes that we want to be aware of. One is vertical. The second one is horizontal. And the third is oblique. And they're going to ask you in this section to identify each one of those. I don't think this section has full-on graphing. That's going to be in the following sections. But we want you to be aware. So I want to break each one of these down and talk about it, and then go through a series of problems that I found in the homework. They do offer you some pretty challenging problems, but challenging not in a bad way, not that it's beyond your capacity, but just good things to look at. So vertical asymptotes, that's where I'd like to start. You have a vertical asymptote. And maybe I shouldn't say you, that sounds kind of funny. You probably don't have a vertical asymptote, but a function, let me get my English correct. A function has a vertical asymptote at each point where the function is undefined. Okay? And so essentially these are where we have domain restrictions. Okay, but I want to be careful about that. This is better stated like this. So let me just make up a function. I told you, and so I'll model that usually they use capital letters when they have rational functions. So I'll put a g of x. And up top I want to put x minus 2, and on the bottom I want to put x minus 3 times x plus 4. So notice that g of x is completely simplified. And so we can see already that it has domain restrictions at 3 and at negative 4. So it's everything but negative 4 and 3. That's the part of the domain. This thing has vertical asymptotes because there are points to which the function's undefined. So this one has vertical asymptotes at x equals 3 and x equals negative 4. Now, what are vertical asymptotes? It's probably bad that they're not having you graph right away as well. Let's take a look at this g of x function. I'm going to show you the graph of it. What I know is, from the top, I know that if I plug in 2, the value is going to be 0. Do you see that happening? G of 2 is 0. 2 minus 2 over some non-zero stuff is going to be 0 over some non-zero stuff, and that's going to be 0, right? And so we get that's where it's crossing right there. Now, what can't happen is this graph cannot go through 2 points. There's no way that it's going to go through 3. And so at 3 we have what's called a vertical asymptote. And then we also have a similar one down here at negative 4. So these pretty much just segment the graph. So when we say a vertical asymptote at x equals 3 and x equals 4, maybe the word at should be replaced with the word of. And I'll put that in blue just to highlight it. These are linear equations of vertical lines. You need the x equals 3 and the x equals negative 4. It's not a single number. It's the line x equals 3 and x equals negative 4. What happens around vertical asymptotes is the graph either shoots up to positive infinity or down to negative infinity. This graph actually has 3 areas that need to be filled in. To the left of the x equals negative 4 line, in between the negative 4 line and the x equals 3 line, and then to the right of the x equals 3 line. That's what we're working on in the next section. But what these vertical asymptotes are places where the graph cannot cross. And because there are places where it's undefined, it shoots either up to, like I mentioned, a positive infinity or negative infinity, because the top is staying roughly the same, but the bottom is getting closer and closer to 0, and therefore getting either really big or really going way up or way down, depending upon the overall sign of the graph in that area. You'll see that better in the next one, but I just wanted to make sure that you knew what a vertical asymptote was, a place where the graph could not cross. Okay. So that's where we have vertical asymptotes. Now, what's interesting about this section, and when I looked at the homework, is the respect they give to that definition. Some books will not get to the technicalities. Our book does. Take a look at a new function, h of x. H of x maybe being x squared plus 3x plus 2. And that's all over x squared plus 5x minus 6. Okay, let's take a look at that. And so I'm just making this up on the fly because I want you to see something that will come up in the book examples. Let's factor the top. The top factors as x plus 2 times x plus 1. Bottom factors of 6 that subtract to be 5. They exist. Negative 6 and positive 1. Now the domain of this function, this is what I want to plant this into you early. The domain of this function is identified right away before you do any simplification. It's a set of all x's such that x does not equal 6 and x does not equal -1. I cannot stress that enough. That's your domain restriction right there. You cannot plug in -1. Now, why am I saying that? You're like, well, Jensen, of course you can't plug in -1. Take a look at this thing. Take a look at the top and bottom. This thing does not have two vertical asymptotes. It has just one. I'm going to come in here using a red pen. These x plus 1's cancel out. What that does in my graph is it puts a hole in the graph at 1. So if this is 1 and the graph is going like this, there's actually a removed hole at, whoops, I should have realized that was going to happen. There's a removed hole at 1, right, if that's what it looked like there. So there's a hole there, and we need to respect that, but it's not a vertical asymptote. So for our purposes right now, they're making sure that we truly understand this. A function has a vertical asymptote at each point where the function is undefined. Okay, maybe I'll make that even stronger. That's good, actually. I'll erase that period. After simplification. So, for example, here the first example we looked at, there was no simplification, but here there is. And so what we have is that this graph looks like x plus 2 over x minus 6. Okay, well, and has a hole whenever x is equal to -1. I apologize. When I drew that graph, I drew it at +1. I should have put the hole at -1. Not worth going back and doing that over, but I'm glad I caught that, so in case it was driving you nuts. It's going to have a hole at -1, not +1. So, where is my vertical asymptote? I have one. I have one vertical asymptote. I'll start labeling them as VA. At the line x equals 6. It'll have a vertical asymptote there and either be shooting to positive infinity or negative infinity on both sides of that, right? And both sides it's going to either be shooting to positive or negative infinity, and we'll see that in the next section. So I want you to be aware that there could be simplification like that. All right. Let's go to the next type of asymptote. The next type of asymptote is a horizontal asymptote. Okay, and here's how you find your horizontal asymptote. It is got through what I call a degree comparison. If the degree of the numerator is, and then case 1, less than the denominator, then you have a horizontal asymptote. Of 0, always. So let's take a look at this one right here. Let's go look at the very first one I did, this g of x function. I'm going to take an opportunity just to get rid of all this so we can highlight that g of x function. If you take a look at the numerator, it's of degree 1. The denominator, if you were to multiply it out, is a degree 2. It's an x squared. So the degree of the numerator is less than the degree of the denominator. This thing has a horizontal asymptote of 0. So what a horizontal asymptote is, when we say it has a horizontal asymptote of 0, we're saying for large values of x, it's going to come to this 0 line. And that tells us a lot. So what we know right now about this function, putting some things together, is at x equals 3, it had a vertical asymptote. At x equals -4, it had a vertical asymptote. It was crossing at 2, right? And passing through that, right? Its multiplicity is 1. It's going to pass right through there. So we would just need to find out where we are. If we plugged in 0 to get our x-intercept, we'd have negative 2 over negative 3 times 4. And so that's a negative over a negative, so that's a positive. So we're up here, passing through this, and going like that. And then we must be, since there's no other 0, coming up to this guy right here. And what's happening out here, if we're beyond 3, everything's positive, and we're looking like this. So notice that we're crossing. The reason why I wanted to show this is we're crossing the horizontal asymptote. So don't get in your mind that a vertical asymptote can't be crossed because it is a domain restriction. A horizontal asymptote is something for large behavior, for end behavior, large behavior, right? And so this thing is looking just like this. That's what this thing looks like. That's what we're going to be doing in the next section. But a horizontal asymptote is something that the graph gets closer and closer to for a large value, both positive and negative, for large values of x. But you can absolutely cross a horizontal asymptote any number of times, and you would be fine. Okay, so we're going to look more at that in the next section, but I want you to know what it is. It's a line that it gets close to. So this one right here, because the degree of the numerator is less than the degree of the denominator, it does have a horizontal asymptote, and the horizontal asymptote is at y equals 0, right? It has a horizontal asymptote of 0. Remember, it had vertical asymptotes of x equals 3, x equals negative 4, and a horizontal asymptote of y equals 0. Take a look at this guy. We know it has a vertical asymptote of x equals 6, but do a degree comparison. You can look at that degree at any stage you want. So you could look at that degree in the beginning, an x squared over an x squared. Degree 2, degree 2. The numerator is not less than the denominator. It's the same. Even here, when we did the simplification, x plus 2 over x minus 6. The degree of the numerator is 1. The degree of the denominator is 1. The degree of the numerator is not less than there. So the horizontal asymptote is not 0. But let's talk about that case. If the degree of the numerator is the same as the degree of the denominator, you have a horizontal asymptote of y equals the ratio of leading coefficients. I'll show you what I mean by that. Let's come back up to this one where we knew that they were the same. You can look at the beginning or at the simplified version. I'll look at the beginning. The degrees are the same. These are the leading coefficients. The ones of the highest degree. The coefficients are the number out in front. You can say there is no number. There is. It's 1. So this one has a horizontal asymptote at y equals 1. So if you were looking at something like r of x is equal to 3x squared plus 2x plus 1 all over 4x squared plus 5, this would have a horizontal asymptote at y equals 3/4. That flat line 3/4 above the x-axis is the horizontal asymptote. So the degrees are the same. It's the probably shouldn't have circled the x squares, but it's the ratio of leading coefficients there, and that's where I'm getting the 3/4. And again, we'll watch this get practice with. The third thing that will that it could be is, so we have the numerator being less, we have the degree of the numerator being the same. The only other one that they care about is the degree, and again it's for calculus, of the numerator. is exactly one more than the denominator. Okay, so let's practice with that. And then if it is, do long division. I know you're not going to like that, but we have to do long division. Okay, so let me show you an example. Let's take a look at this function. R of x is equal to x squared plus 2x plus 3 all over, actually let me do 2x squared plus 2x plus 3 all over x squared. Actually, let me do it like this. I'm going to take a step back. All over x cubed plus 1. So if you can tell between a horizontal and oblique by doing a degree comparison, because the denominator has a bigger degree, because the degree of the numerator is less than the denominator, this has a horizontal asymptote of y equals 0. So if the bottom's going to win degree-wise, you're going to 0. If the bottom is bigger than the top, you're going to 0, regardless of how much it's bigger. You are absolutely going to 0. I'll look at q of x equaling 2x squared plus 2x plus 3 all over x squared plus 1. This thing as well has a horizontal asymptote, but it's not 0. It's at the ratio of leading coefficients. The degrees are exactly the same of top and bottom. And so it has a horizontal asymptote of y equals 2. You see that happening? We recognize that they have the same degree. Anytime they have the same degree, it's a ratio of the leading coefficients, the coefficients of the biggest terms, and that's a 2 to 1 ratio, and that's where we're getting the 2. F of x, 2x squared plus 2x plus 3 all over x plus 1. In this case, you're a little bit sad. The degree of the numerator is bigger, and unfortunately just by 1. Whenever that happens, you have a little bit of extra work to do. You have an oblique asymptote. So this one definitely has an oblique asymptote. You won't have a horizontal and an oblique. You either have a horizontal, or you'll have an oblique only, or none. There's plenty that have none. Let me give you an example of something that has no horizontal or no oblique. I'll call it r of x again. 2x cubed plus 2x plus 3 all over x plus 1. Notice that the degree of the numerator is bigger, so it's not horizontal, because horizontal needs either the bottom to win or to be tied in terms of a degree comparison. It's not oblique because it's not exactly one bigger. We wouldn't list any horizontal or oblique. Oblique asymptote is a line. Okay, so this has no horizontal or oblique. Okay, so that happens a lot. But this one does. So whenever this happens, you have to do the long division. What do you mean long division? I mean long division. And your oblique asymptote will be sitting right here. So I got to take x into 2x squared. So that's 2x. And I get a 2x squared plus 2x. And I do a subtraction. Okay, so I subtract off. And what do I get? I get nothing. That's good. And a remainder of 3. Now x won't go into 3. So this is your oblique asymptote. You could care less about the remainder. So the oblique asymptote is y equals 2x. And what we're going to have in subsequent videos and things is some examples from the homework of this. But I just thought I needed to give you an overview of what these asymptotes are. So again, we have 3 types. Vertical, where you have domain restrictions that can't be gotten rid of. Horizontal, where the degree of the numerator is either less than or equal to the degree of the denominator. And oblique, where the degree of the numerator is 1 bigger. And so you'll get really good at this. Don't be panicked if it's not sitting well right away. You have sections worth of work in which you can do this. And it has really good implications for understanding things like limits and other calculus concepts that will come in your next class.